Okay, as I just said, a lot of times this is tough to integrate and this is easier. Sometimes you want this, okay? But it's hard to integrate, but this is easier. And of course, sometimes neither one of them's easy, okay? But many times, one or the other is going to be easier, so you can use one to evaluate the other because one of these or the other tells you what you really want to know, okay? And similarly over here, same thing. Okay, so let's just look at a picture. Let's say you've got a simple region. Maybe you've got a circle or an ellipse down here in the plane, okay? And then you've got some surface whose boundary is that circle. So you have a closed region, right? And you want to integrate the curl around this, through this region. Now you have your function f, your field, whatever it is, right? And I mean these to kind of be in the plane and not to all be tangent to that boundary, okay? Well, you know, whatever this f is doing on the boundary, you're going to have a component in the direction around the boundary, okay? Around the curve that bounds this circle down here, okay? So that circle is a boundary of this region. Now you could use any figure. You could use a circle up here as your boundary. Well, actually you couldn't, but okay. Anyhow, you can use this whole upper region as your boundary if you didn't know what was going to happen down here in the circle, but usually that circle would be simpler. And that doesn't necessarily tell you anything you need to know. Then you got the curl, okay? So the curl is up here, and the curl is doing something else. Through space. Okay? It's also doing something down here in this boundary, right? So you can figure out what the integral of that curl is over the whole surface, including both parts of the boundary, right? By simply integrating around the boundary. Integrating the tangential component of the function around the boundary.
Just
Okay.
a circle?
Could be anything. I drew a circle, but maybe it's an ellipse, and maybe it's distorted somehow, and maybe it's actually a really complicated, ugly-looking surface that you never want to even try to parameterize or region, okay? Of course, if you're going to do this, you're going to have to parameterize the region, okay? But it may be already parameterized. Maybe it's just some polynomial in x and y, okay? Or something of that nature, okay? Now, the point I'm trying to make here is, okay, this is one surface bounded by this curve. So let me just make that surface blue. Okay? But it's bounded by this ellipse or whatever it is, right? Well, if I can do this integral, that tells me what the curl is over this whole thing, right? Now, if and your book has a better picture, if I draw any other surface bounded by this thing, the integral of the curl is the same over that surface.
What does the curl represent, like in fluid mechanics.
We've talked about it, but I'm not going to, it's circulation.
Okay, yeah.
Circulation around a point. Think of water going down a bathtub. So, okay? And your book has a good picture. And I can't draw the picture, but it just says, you got a little paddle wheel and you put it at various points in this fluid or whatever it is, if you imagine it in terms of a fluid. And it tells you how fast it's rotating, if it is rotating.
Okay.
If it's a laminar flow, it won't rotate, no curl. Okay? Laminar wasn't the right word, but I still get the idea. So, I could draw another surface. I don't know. Any old surface that's bounded down here by this circle. And the curl over that surface is the same as the integral of the curl over this surface is the same as the integral of the curl over this surface. So the integral of all surfaces bounded by this little shape, wherever it is, it doesn't have to be in the XY plane, it could be anywhere. Okay, and it doesn't have to be in a plane, it could, do this sort of thing. All surfaces bounded by that, you get the same integral for the curl.
Huh.
Okay, so the integral of the curl over the surface is surface independent. Depends only on the boundary, which is pretty neat.